How can two dice model the spread of a disease? In this SORBET and SLS simulation, each contact produces a dice sum. A selected contagious sum allows infection to pass from an infected person to a susceptible person. Your job is to change the probability, observe the evidence, and explain what makes infection more or less likely. Start by noticing the main parts of the screen. The canvas represents a closed population. Blue people are susceptible and red people are infected. The model is SI with no recovery, so an infected person remains infected. The live variables show dice outcomes, contacts, successful transmissions, and the changing population totals. First, set a population. Then clear every contagious sum and start the simulation. People can still meet, but no dice result is defined as contagious. Watch the contact count increase while the infected total stays at 1. This baseline matters because it shows that contact alone is not enough in this model. Reset, then choose contagious sum 7. 7 is useful because 6 of the 36 possible dice combinations produce it. Start the simulation and watch for susceptible people to become infected. Compare the infected count with the baseline. A contact can now transmit disease, but infection is still not guaranteed. Turn on pause with each contact. When two people meet, the simulation stops so you can inspect the dice sum and the last contact message. Ask 2 questions. Did the contact involve an infected person, and was the dice sum one of the selected contagious sums? Both conditions are needed for a new infection. Now choose 7 and 8 together. This creates 11 contagious outcomes out of 36 instead of 6. Run the model again and compare the rate of increase. Selecting more likely outcomes does not force every contact to transmit infection, but it raises the probability and usually produces a faster spread. Open activities 2 and 3. The possibility diagram lists all 36 dice combinations. The middle sums occur more often than the extreme sums. 7 is the most likely individual sum, with probability 6/36. Use the observed count column to compare experimental results with theoretical probability. Activity 4 collects infection data by stage and graphs total infected against time. Look for the overall trend rather than one unusual contact. Then repeat the investigation with a different population or contagious sum selection. A productive comparison changes one factor at a time and uses the table and graph as evidence. The final activity asks you to evaluate the model. Real disease spread also depends on distance, duration of contact, immunity, behavior, ventilation, recovery, and many other factors. This simplified model is useful because it isolates probability, but a good scientific explanation must also describe its assumptions and limitations. The teacher analytics panel records actions in sequence with relative time and the state after each action. It helps a teacher see whether a student tested a baseline, compared probabilities systematically, and inspected a contact before drawing a conclusion. The log can be collapsed or cleared for a new investigation. Your challenge is to complete all 5 simulation marks, compare one contagious sum with 2 contagious sums, and explain the difference using probability. Then write one limitation of the SI model. The simulation and worksheet resource links are in the description. Pause, predict, test, and use evidence before you decide.